Hello, my name is Steven, and I'm going to be making up the differential equations video. How about we get right into it? We're going to talk about definitions and terminology. If you don't know the vocabulary, you can't possibly understand differential equations. Now we're going to talk about classifications of differential equations. I'm going to mention two types of differential equations. The first one is going to be an ordinary differential equation. And the formal definition that I can think of is the following. If an equation, and I'll explain everything that I'm saying, contains ordinary derivatives, first derivative, second derivative, third derivative, not partial derivatives, of one or more variables. But with respect to a single independent variable. Then we call this type of equation an ordinary differential equation, also known as ordinary differential equation, OD. Of course, let's look at some examples. An ordinary derivative with respect to a single independent variable, x, plus 8y squared d squared y dx squared. This is equal to 7e to the x. That is an ordinary differential equation. Because every time you have the derivative, it's ordinary, it's not partial, and it's with respect to one variable, x. Another one might be dy dt plus dx dt plus y is equal to 3x. These are ordinary derivatives and not partials, and they're with respect to one independent variable, c. Okay, the words above, maybe they bother you, fine. Another example might be d cubed x. Well, let's make it d cubed y dt cubed minus 3 dy dt is equal to 4x dx dt. All the derivatives are ordinary. This is the one that I just circled is the third derivative of y. The second derivative of y. Sorry, the first derivative of y. The first derivative of x. All with respect to the same letter. all with respect to the same letter. In this last case, t. Now, let's try to just modify this one that we have in front of us. An equation contains, if an equation contains partial derivatives of one or more dependent variables, so let's see what we can do here. Maybe we'll get rid of this. This should be two or more dependent, hold on. No, I'm trying to save time and let's just do it. Sorry. An equation involving the partial derivatives of one or more dependent variable of two or more independent variables is called a partial differential equation, also called PDE. An example might be, write it down more clearly as a partial. The second partial of u with respect to partial of x squared, partial squared u, partial y squared equals 3. This is an example of a PDE. I'm taking partial derivatives with respect to two variables, two independent variables, x and y. Partial squared u, partial squared x, plus partial squared u, partial squared s. This is equal to 4 partial u, partial s. These derivatives are all partial, and they are with respect to two or more independent variables. If there was only one independent variable, then they wouldn't be partial. Right now in the bottom we have u as a function of x and s. That is, whatever u equals, you expect to see x's and s's. It might not even have x's. It might not even have s's. 3x squared. It can have none of them. I mean, after all, we've all seen function of x's that didn't have x's in it. It's a constant. But what you can expect is not to have any letters other than r and s. Now, if u is just a function of x, then you can take a partial with respect to x. You can only take partials with respect to x if u has other variables, if u is a function of two or more variables. We'll get simpler as we go on. Let's talk a little bit about notation. I threw some in already, hopefully you knew what they meant. dy dx, that of course can be denoted by y prime. d squared y dx squared can be denoted by y squared. Sorry. Y double prime. d cubed y dx squared dx cubed can be noted by y triple prime. Generally, when you take more than 3 primes, say the fifth derivative of y with respect to dx to the fifth, if you have that one, you're not going to go 1, 2, 3, 4, 5. I mean, what if it was 12? 6, 7, 8, 9, 10, 11, 12? No. If it's more than 3, you put a 5 up here because it's fifth, and in parentheses. So in general, the nth derivative of y with respect to dx to the n, this would be denoted like this. Not like that, not like that. No. This is not correct. That is, you have to put the brackets. The brackets say you mean derivative. You mean derivative. You probably won't see this, but it's valid. That would mean the second derivative. The next thing that we should talk about is the order of a differential equation, whether it's an ODE or a PDE. Classification of the order. If you have 3x d squared y over dx squared plus 4dy dx equals 7, I look at my derivatives. This one is of second order. Why? Because it's the second derivative. This one is the first order. The whole equation is, this whole equation is a second order ordinary differential equation. It's an ODE because these are not partial derivatives. Now, you remember before, years ago, you needed to decide what the degree of a polynomial was. And the answer was, it was the highest power of x that you saw, or the variable was y, it was the highest power of y that you saw. It's the same thing with differential equations. And they talked about an order that's very similar to degree. You just look at the order of the derivative. Now, if I modify this problem and I say times d cubed y dx cubed to the fifth power, this is a third order ordinary differential equation. This 5, it has nothing to do with whether we're taking the first derivative or the second derivative. And think about it. The second derivative cubed is not the sixth derivative. 2 times 3 is 6. It is not that. It is not that. You compute the third derivative, which might be 3x. And then you raise that to the fifth power. So you just look at the degree of the derivative. It's 2 and understood 1 and it's 3, so it is third order. And since it's ordinary derivative, it's third order ODE. The next thing we'll talk about is whether or not it's linear. Okay. Just erase this, please. Now remember, when it came to ordinary equations, notice I didn't say ordinary differential equations, regular high school equations, basic algebra equations. It was linear if the degree of the x was never more than 1. If the degree of x was never more than 1. Now we're going to just talk about the degrees of the derivatives. Whether it's the first derivative or the second, this second derivative right here is being raised to the first power. This first order derivative is being raised to the first power. This third derivative, it's being raised to the fifth power. This is not linear because that's not 1. If there were no exponent here, just like there wasn't 1 here or here, it's understood to be 1, and then it would be linear. And you can have 7x to the 5th, and this is still linear, because all these powers that I'm erasing are understood to be 1 for the derivative. We're talking about the power for the derivative, not the power of x, not the power of y, just the powers of the derivative. They are all understood to be 1. Do not say, but come on, there's a 2 there. That's y double prime, and it is being raised to the first power. This is 3x to the 5th y prime, y double, 3x to the 5th y prime, minus 4y prime. Now, let us put this 5 back here. Equals 7x to the 5th y cubed. Now, y cubed, I can use the prime notation. Y cubed is being raised to the 5th. This y double prime to the 1st. This y prime to the 1st. This y cubed to the 5th. This is not linear. This is not linear. Okay, do not think that y cubed, whether I put it that way or I put the slashes, y cubed to the 5th is not y to the 15th. Yes, y cubed to the 5th is y to the 15th. These brackets say a lot. They're saying the number in there is the number of times we're taking the derivative of y. It's notation. This completes the section on definitions and terminology.